This is the beginning of week 3 of PHY1020, Conceptual Physics. This week we're going to be talking about conservation laws. On the request of many students, I've endeavored to cover the material in several parts. So the lecture will be broken up into several parts, and there will be puzzles on each of those parts. All right, let's get going. So we're going to be talking about conservation laws. What is a conservation law? It's a law of nature. It's not a law of humans, although humans discovered those laws, or physicists and scientists discovered those laws. So in physics, a conservation law is a law of nature. It's a law of the universe, if you will, that says that a particular physical quantity does not change or does not vary with time. What's a conserved quantity? Well, conserved quantity will be one such physical quantity that does not change with time. Sometimes one says conserved quantity, sometimes one uses the expression invariant. Invariant means that a quantity is not changing with time or is not changing with some reference frame. We will see that there are actually very many laws of conservation in physics. We will see several this week, and as we progress through the semester, we'll encounter a few more. But essentially, studying physics amounts to discovering what are those conservation laws, what are the forces, what are the symmetries, what are the things that are conserved in physics. And it turns out that there's a deep and subtle connection between conservation laws and the symmetries of the universe, the physical symmetry, the spatial time symmetries, as well as other types of symmetries, that some of which we will discover throughout this semester. So we're going to this week we're going to discover and discuss some of these symmetries of nature. One particular symmetry that we use or we encounter a lot is the conservation of mass. Essentially, conservation of mass means that the total mass of a system, or of an isolated system, I should say, is constant. That is, it doesn't change with time. It doesn't change when things are happening within the system. It also means that no matter is added or removed from the system, from whatever environment the system is in. So no matter enters or leaves the system. That's what isolated system means. And if you have an isolated system, then the mass of this system will not change. To first approximation. It turns out that nature is a little more subtle than this, but by and large, conservation mass is a good or a reasonable approximation to the conservation of energy, and as such it is to be considered a law of conservation, a law of nature. It applies in everything that we encounter in our daily lives. However, it doesn't strictly apply when you encounter chemical reaction or nuclear reaction that can release, for instance, radiation. So there are chemical and nuclear reactions that can exchange energy in the form of radiation, in the form of infrared, in the form of gamma rays, in the form of light, with their environment. They can be provided or supplied light or this form of energy, or they can produce this form of energy. So in general, we will see that what is conserved is energy, not mass. And so, as a prime example of this is the notion, you are all familiar that water the chemical formula H2O, 2 hydrogen atom for one oxygen atom. But it so happens that 2 molecules of water, 2 molecules of H2O, which is 4 hydrogen, 2 oxygen, are not equal to the mass of twice the mass of H2 and 1 time the mass of O2. Because there is a binding energy, there's a chemical binding energy, and that means that the mass is not strictly equal, but approximately equal. Let's move on to more important or more useful in general laws of conservation. The first one we encounter is known as linear momentum conservation. Okay, so let me introduce the concept of linear momentum, or in general people just say momentum, they don't say linear momentum, although we will see later in this lecture that there's a connected concept called angular momentum. But in general, people will say momentum as opposed to angular momentum. It's particularly in English or in American English, scientists don't use the phrase linear momentum, although it is used in other languages, particularly in French. Linear momentum is denoted by the symbol P for historical reason, and one can calculate or define momentum as the product of the mass of an object times its velocity. So you will know that P is adorned with a vector or with an arrow. So P in the momentum is a vector, and it is equal to m, the mass of the object, times its velocity. So vector P equals m times vector V, which means that the magnitude of P is determined by the mass times the magnitude of V, and the direction of P is determined by the direction of V. Now you will recall the Newton's second law. Force F equals mass m times acceleration a, which one can also rewrite as m times the ratio of the change in velocity delta v over the period of time delta t required to accomplish this change. We can also write a change in momentum, and so we will write delta p. Delta p will mean change. Delta stands for change, so change in momentum. And so the mass will not change, at least in general, or in most cases, so we can assume the mass is constant, thus conserved. And so we have that delta P equals m times delta V. The change in momentum is equal to the mass times the change in velocity. You will note again that we have vector quantity. So the magnitude of delta P is equal to the magnitude of m times the magnitude of delta V, and the direction of delta P is the same as the direction of delta V. Having introduced this change of momentum delta P, now we can identify that in the second law of Newton, there is a product of m times delta V. And so we can thus rewrite Newton's second law as F equal delta P over delta T. As it happens, it's the more correct way of writing Newton's law. It is the more correct way of doing this because this particular formulation of the law will enable the solution of problems where the mass could be changing, whereas F equal ma, the simpler formulation, does not enable that. So F equal delta P over delta T is the better way of writing Newton's second law. So I've said that momentum is a conserved quantity, so let's talk about that. So conservation of momentum is what we have when the force is the force applied onto a system. The net force applied onto a system is 0. So F being equal to delta P over delta T. If F is 0, meaning 0 magnitude, whatever and the direction becomes irrelevant here, then delta P over delta T is 0, and that implies that delta P, the change in momentum, is also vanishing. It's also 0. So we can summarize this by saying the net force applied to a system is 0. When the net force applied to a system is 0, the momentum of the system does not change. It is invariant. Let's consider an example of this. First, with the concept of momentum. So consider a bicycle plus rider with a total mass of 80 kilogram going at a speed of 10 meters per second. You can ask yourself, what is the momentum of the bicycle plus rider? Well, the mass is 80 kilogram. The velocity, or the speed, is 10 meters per second. We just multiply the two numbers. We get 800 kilogram meter per second. And the direction will be whatever is the direction of the bicycle and its rider. Consider a second example, that of a car plus passengers with a mass of 1,200 kilogram with the exact same speed, that is 10 meters per second. What is the momentum? The car's momentum is then 1,200 kilogram times the speed of the car, assume here to be the same, 10 meters per second. And so 1,200 kilogram times 10 is 12,000 kilogram meter per second. You can ask yourself to try to figure out what is it that momentum means. So consider that you would have the bicycle plus rider and the car to have the same momentum, right? So let's assume the speed of the car is 10 meters per second. How fast would the bicycle need to go to have the same momentum as the car? Well, you find out that it would have to have a speed of 150 meters per second. So what momentum means is that it's a quantity, it's a physical quantity that depends both on the mass and on the speed of the object considered. So let's come back to Newton's second law for a little bit. We saw that to change an object, one has to change an object's velocity, one has to apply a net force onto that object. So in the context of the concept of momentum or linear momentum, it means that to change an object's linear momentum, or just momentum, one will need to apply a net force on that object. Evidently, the larger the force, the faster the momentum will change. If the mass of this object is remaining constant through the process of accelerating this object or applying the force onto the object, the equation that we just saw will become equivalent to the first form of Newton's second law. So specifically, I can write that F equal delta P over delta T. Delta P is, as we saw, P is mv. So delta P is the change in mv. If the mass is not changing, then I can factor it out. And so I have that F is simply m times delta V over delta T. And we saw that delta v over delta t is simply the acceleration of the object. So we see that whenever we have cases where the mass of an object doesn't change and it's subjected to net force, then the first and second formulation of Newton's law become completely equivalent. If the mass is changing, it is not easy or simple to use F equal ma, and in fact it becomes then much easier and much more practical to use the second form of Newton's law, which is F equal delta P over delta T. As it happens, much of what we do involves changes of mass. If you're driving a car, you press the accelerator, that leads to the injection of fuel into the engine. You burn this fuel to generate a rotation of the engine. It generates what we call a torque, something we'll talk about later in this, briefly later in this lecture. And then the engine makes the wheel spin and you accelerate, right? So, but when you press the accelerator, you're consuming gas, you're consuming fuel, you're burning fuel. So that means the amount of fuel in the car is changing. And so strictly speaking, to solve a problem in that context would mean that you would have to use the second form, delta P over delta T, because F equal ma is not strictly applicable since the mass is constantly changing as you burn fuel. Now, the mass of fuel that one burns at any given time is relatively small, so F equal ma might still be valid and useful. Now, there are cases, more extreme, where this is not true. For instance, when NASA or other space agencies launch rockets, they end up burning fuel at a rate which is enormous, which is very, very high, and that means that the mass of matter within the rocket is changing dramatically fast. And so to consider the physics of a rocket, what's happening when we launch a rocket, one has to apply the second form of the law, F equal delta P over delta T. Let's consider another example. This one involving a collision between a tennis ball and a racket. Well, it's a collision that is induced by the player. So let's consider a tennis ball with a mass of let's say 0.06 kilograms, 60 milligrams, 0.06 kilograms. And let's assume that it leaves the racket with a speed of 40 meters per second, corresponding to 90 miles per hour. To see what's happening when a tennis player, particularly professional tennis player, hit a ball with their racket, takes a very keen eye. It's the collision is very short in time, very, very short indeed. In fact, I would probably not believe anybody who says that they can see what's happening in detail during that collisions. So, but as it happens, we today now have all kinds of technology, and one can take slow motion pictures of a racket hitting a tennis ball, and it's as shown here. And what you see in this collision here is that the ball which is elastic, the ball is really squeezed by the collision with the racket. It's hard to see, but the net of the racket is also pushed back. And because the ball is elastic, it will recover its shape, and as it recovers its shape, it will be propelled by this, and then it can reach then fairly high velocities, so for instance 40 meters per second. What this high-speed video tells us, however, is that, or videos like this one tell us that the interaction between the racket and the ball is very short, and it can be as short as 0.005 seconds. And so that means that there is a change in velocity going from essentially 0 to 40 meters per second in 0.005 seconds. So that's a pretty dramatic acceleration. And I invite you to calculate it for yourself, and you'll see that it is a very, very large acceleration indeed. And that's why the ball is dramatically squeezed and deformed in the process. So let's expand on this a little bit. Because the ball starts with 0 horizontal speed and hence 0 momentum, its change in momentum can be calculated as delta mv. Delta p is delta mv, which will be the mass, 0.06 kilogram, times the change in speed. It starts from 0 and it reaches 40 meters per second after the hit. So the change in delta v is 40 minus 0, the final minus the initial velocity. So that's 40 meters per second times 0.06 kilogram. That gives us the change in momentum. That's 2.4 kilogram meter per second. As it happens, this quantity, delta mv, is known as the impulse given to the ball, or given to any object that would be accelerated in a similar fashion. This impulse then is 2.4 kilogram meter per second. Now we said that F equals delta P over delta T, so which in this case becomes delta mv over delta T. So that means that we have a force of 2.4 kilogram meter per second divided by 0.005 seconds. That amounts to 480 Newton. Right, corresponding to about 180 pounds. So it's a pretty large force applied on this fairly small mass object. Let's expand a little further on what I said earlier about vehicles and things that change mass as they accelerate or decelerate. Obviously, cars burn fuel, planes burn fuels, boats also burn fuels, and of course the archetype of quickly burning fuels are rockets. And this here shows a picture of a launch of the space station, one of the space stations that was operated by NASA for several years. So what happens here is that the rocket injects fuel into the reaction, if you will, the reaction vessel. The fuel is burned. In some cases it involves a chemical reaction with oxygen. Sometimes it involves two chemical substances that when put in contact will have a violent chemical reaction, so-called exothermic reaction. And so a lot of the energy is very suddenly released. That leads to a quick, very, very quick and dramatic expansion of the gas. And the gas cannot be expelled in any other direction than the back of the rocket. And so the gas then is forced to be expelled at very high speed in large quantity towards the back of the rocket. And pushing the gas means that we have an action. Essentially the rocket or plane is pushing onto the gas, but remember, action equals reaction. So the gas itself is resisting this push, and what that means is that the gas itself ends up pushing on the rocket. And so gas is expelled one way, the rocket is propelled the other way. And in this process, there's a lot of energy being transformed, chemical energy being transformed into thermal energy of the gas, and this energy propels the gas out at the back of the plane or the reactor or engine, and then the motion of the gas then is what propels the exit, the pushing out the gas is what ends up producing the reaction of pushing forward the plane. Fuel is also burned in cars. That's typically not a big thing when it comes to car, for instance, collisions. However, there's always momentum conservation when two cars collide. Evidently, right after the collision, those cars are also on the road, at least most of the time, and so there will be friction of the road, which may complicate the problem a little bit. But momentum conservation is something at play in collisions. So we'll stop here and come back in a moment with the part 2 of this lecture.